the lacunae. And our bones, for postcranial, our bones are formed in cartilage, and then they become bone. They're slowly mineralized, and we'll talk about that. And so you can see how this growth is happening, appositional growth, meaning from the outside to the inside. And so we'll talk more about that. Just, I want you to get that word in your mind, appositional growth. I want you to kind of pay attention to this layering that the cartilage is having as it's growing. These would be the chondroblasts. So these are the unformed cartilage cells, and these are the chondrocytes. So these would be the mature cartilage cells. And then, of course, here's all those elastic fibers, and you can hardly really even make out the picture. And then, of course, this is the fibrocartilage, the elastic fibers and the fibrocartilage, and which is just more of these types of fibers. Any questions so far? And this hyaline, I think you really should learn to recognize hyaline cartilage. I mean, you're going to see this in the microscope, and when we do look at the microscope in the lab, you will see hyaline cartilage. It's one of those tissues that you will eventually get to the point where you'll recognize it right away, because there's so much of it around the body. So this hyaline, the chondrocytes, and this hyaline matrix, which he said was hyaluronic acid. I think that's a popular supplement people take for joint damage and joint problems, is hyaluronic acid. Fibrocartilage, the chondrocytes, so these mature cartilage cells in the matrix with collagen. I'm sorry, I am kind of a fuss with techno. I'm getting better. It's hard for me. And then elastic is this elastin. These elastin fibers are so important. And here again is another picture that you can see a little bit more clearly the different types of configurations that you'll see in these types of cartilage. And I love that elastic ear epiglottis. I love that. I love learning little things like that. So I think that's one of the questions on the test, so nobody should miss that one. Because with E, remember? Okay. So here's some hyaline cartilage. The costal cartilage that you all looked at last week, that's hyaline cartilage. Okay, it's not very strong, but it's well formed. But I mean, you could break it. The fibers, fibrocartilage is going to be a little stronger. Hyaline cartilage, smooth, glossy, but not a lot of strength because it doesn't have a lot of fibers in it. It has fine collagen fibers. You can see here, you can see it in this developing fetus. Our bones, when they are developing, we'll talk about this cartilage model, and again, you'll get to see hyaline cartilage. And so perichondrium is always surrounding the cartilage. This peri, meaning around the chondrium, perichondrium. And it's usually a dense, irregular tissue. So this is where the appositional growth is coming from. Just, I'm kind of jumping forward here a little bit, but remember that cartilage doesn't have any blood, right? There's no blood supplying cartilage. So how is that cartilage how's it gonna grow? How's it gonna get nutrition if there's no blood, right? So it is from this perichondrium, which has this dense, irregular tissue. And that's where you're gonna get the blood supply that is gonna feed the cartilage, but very slowly, because cartilage is avascular. I mean, that's kind of it works great, and it cushions our joints, it makes everything move smoothly, but it has everything is always a trade-off. So then we have this fibrocartilage, thick bundles. Chondrocytes are clearly visible again. You can see them here kind of in the lacunae. You see how you're just getting those chondrocytes are still in the lacunae, just like the hyaline. Only now they're kind of surrounded also by a lot of fiber. Intervertebral discs, pubic symphysis, the symphysis here in the clavicle, and it's the strongest type of cartilage. Meniscus, the meniscus, we have these little pads in our knees, and that kind of help cushion the joint, and those are fibrocartilage. And then elastic cartilage, like the ear. So here is the elastic cartilage, thread-like network of elastic fibers. And the perichondrium is present. So there's the perichondrium. You see the red line up above with the blood supply in there. So that's going to be the perichondrium. It's going to give nutrition to this type of cartilage slowly, but it will get some nutrition. Okay, so that's it for cartilage. Any questions about that? Okay, let's move on to bone. Okay, so in bone, we have these osteocytes, which are in the solid matrix, mineral salts, proteins. We have two different types of bone, compact versus spongy. And we have this Haversian system, which I'm going to show you in detail. And of course, bones are supportive and protective as well. And so our bones protect our organs, they support our bodies, they allow us to have movement. If we didn't have our bones, we'd just be a pile, kind of a muddy pile. So here, this is a kind of a diagram of the microscopic structure of bone. So this is called the Haversian system, where you see this blood vessel surrounded by the lamellae here, and then inside each of these lamellae you have the lacuna. So this which is now we have the osteoblast now formed an osteocyte, and as it started laying down all this collagen, it traps itself. It becomes trapped, and as it becomes trapped, it forms these. Here's a picture of it. Here's a picture. So as the here is the osteocyte, and it starts laying down this calcified matrix of collagen and minerals, and as it does so, it literally walls itself in, and then you have this. You have the lacuna, you have the little osteocyte in the lacuna, and then it has little canaliculi, which are these little canals so that the osteocytes can talk to each other. Because now they're like in these like caves. They've walled themselves into a cave, and the only way they can talk to the cell next to them is through this little caniculi. So it's kind of interesting. And then as this is laid down, and I have a wonderful video to show you about bone growth. I don't know if we'll get to it today or not. And then you have these, so here are the blood vessels, and these are Volkmann's canals, or these perforating canals, and then we have the Haversian canal, another word is central canal, inside each of these lacunae. And so when the bone is laid down, it's kind of laid down in this kind of circular pattern. And so, let me get a pointer. But so you can see this circular, pattern here. As it's laid down, it forms these circumferential lamellae. It forms these lamellae, or these layers. And then as the bone is growing, now we have two ways that bone grow. So bones can grow in length and they can grow in diameter. And it's a very different type of process of growth. When bones grow in diameter, it's appositional. So we just talked about that. What does that mean, appositional? From the outside, right? So when a bone grows in thickness, it's growing from the outside. When it's growing in length, it's growing from the inside. And you could also think of that as endogenous from the inside and exogenous from the outside. Endo, exo. Endocrine, exocrine. You should be familiar with these. Hopefully you've got some of these terms down. And then you have the little caniculi. And then you can see out here in this edge, you can see that the lamellae are kind of broken down. And that is exactly what happens as the bone grows. These lamellae kind of fall apart, or they're, remodeled. Because bone is one of the fastest growing tissues in our body. Think about it. You break a bone and in 6 weeks it's healed. Your blood vessels, or your blood, lasts 120 days before you have a new red blood cell. So your bone is even growing faster than your blood cells. A very fast growing tissue. Probably one of the most dynamic tissues in our body is our bones, which we don't think of as being real dynamic. We think of our muscles as being dynamic, but bone is very, very dynamic. Bone tells the history of a person. I can tell by looking at bones, you can tell if someone was right-handed or left-handed. You can tell whether they did a lot of upper body work, or I had worked on a case once where we thought the girl had ridden, might have been riding on motorcycles a lot, because we could see some extra bone growth in her pelvic, or extra heaviness in her ischial tuberosity, and we thought maybe she might have been, it was just one supposition. She also had a lot of upper body spurring and things like that for her age on the bones that kind of led us to believe that she might have done some kind of manual labor with her upper body. So bones really tell us a lot about a person, and it's because of this dynamic growth. And when we talk about bones, we'll go into more detail. When we look at bone in a microscope, this is human bone tissue. It looks like this. And you see this central canal, the lacunae, the lamellae, and the osteocytes. Any questions so far? We'll go into more detail about bone development as we go on in the semester. Okay. And so then let's talk for a minute about blood, connective tissue, vascular tissue. I mean, we're pretty familiar with blood. We always think of blood as being primarily the erythrocytes. These are the red blood cells. But I actually think that everything to this side is way more important in a way. I mean, I kind of think, we think of blood as red blood cells, but really blood is 45% red blood cells and 55% plasma. And the plasma contains the eosinophils. This is what rushes in when you have an allergic reaction or you have an injury. You get all these eosinophils rushing into the site, and the neutrophils and the monocytes and the thrombocytes. These are what's going to help your blood form a clot. So we have these different elements of blood as a connective tissue. So it's kind of interesting. And we'll talk more about blood later when we do cardiovascular, but just giving you how it is a connective tissue. Thermoregulation. Your blood is what's keeping your body at 90.6 thereabouts temperature. The blood it has its origin inside the red marrow of your bones. It is your kidney that tells the red bone marrow to make more. The erythropoietin is one of the hormones from the kidney, says to the bone, okay, make more red blood cells. So, our bodies really work it's like a big orchestra, and so everybody has their part. And then muscle tissue, of course, is another one of our connective tissues. It has a maximum of intracellular material. These elongate fibers. Irritable, meaning it's very sensitive to electrical impulses. We think a thought and it appears on our face. We barely think about an arm moves out. So it's very irritable, meaning it's very quick to respond to any sort of electrical charge from our body, chemical electrical charge from our body. It contracts. Muscles only contract. Muscles don't expand. So if I want to pull my arm up, I can relax the muscle now. But if I want to pull my arm back down, I have to tighten another muscle to pull my arm back down. So muscles only go one way. They only contract. That's all they can do. We have different types of muscle tissues. Oh, this is very interesting. Okay, so after birth, amitotic. Who knows what that means? What does that mean? If something is amitotic, what is it? It doesn't divide, right. So when you're born, those are your muscle cells. You're not going to get any more muscle cells. When you're born with the muscle cells that you have, you do not develop more muscle cells. Now those cells can get larger or smaller. They can hypertrophy or atrophy. Hypertrophy, they can get bigger, and atrophy, they can get smaller. And we have these things called satellite cells that help to repair muscle cells. So if we damage a muscle cell, we can repair it, you know, but we can't build a new one. So when you're working out and buffing up, what you're really doing is just enlarging the cells you already have. And if you have an injury such that it kills those cells, I mean, I can think of, you know, some injuries that people can get that would kill those cells and they won't grow back. Your other cells will compensate, you know, but, so they're amitotic, and that's important to understand about muscles. And of course, you know, we have 3 different types of muscles, which I think is the next slide. We have cardiac muscle, we have visceral muscles or smooth muscles of our organs, and we have skeletal muscles. Now the skeletal muscles are the ones we always think of, because that's the muscles that we see on our arms, legs, skeletally. Cardiac are involuntary, so skeletal muscles are voluntary, meaning we consciously move them. Cardiac muscles is a specific type of muscle. I'll show you a picture of the cardiac muscle. It is kind of a branch, it's kind of branched. And they're involuntary, kind of working on the heart has its own electrical current. They are striated, so we look for the striation in muscles, and cardiac muscles are striated. Visceral muscles are the muscles of around your arteries and your stomach, and all your organs have, everything has a muscle. Remember, that was something that you had to have to make an organ, was a muscle. And this smooth muscles or visceral muscles are kind of spindle shaped. And so when they contract, they kind of twist up like this in kind of a ball, instead of like cardiac muscles and skeletal muscles just kind of shorten and lengthen, and smooth muscles kind of ball up and stretch out. So I'll show you some pictures of those. And then skeletal muscles, and these are, you know, things that you would find in skeletal muscles. So let me show you this picture. So this would be a skeletal muscle. These are the nuclei. And here, skeletal muscle has a lot of mitochondria, very heavy with energy, so it needs a lot of mitochondria. You have a question? Anyway, these are the nuclei, are located kind of in between the fibers. Then the middle one is smooth muscle, and you can see it's more spindly shaped. And there you can really kind of, you can just kind of tease the part. You can see the nucleus here. And then cardiac muscles have this branching pattern, and there are these little discs in between each one of the cells in cardiac muscle with a gap junction. Remember the gap junctions that we talked about? And that's because it can control, our heart muscle has to, it's a very controlled contraction. We don't want the heart to just wildly start contracting. We want it's a very controlled contraction. This contracts and this, and as the electrical impulses into the heart are very, very controlled and regular. It's really quite beautiful, I think. The whole system of the heart is just it's just amazing. It's like a whole universe in our body. Somebody have a question? Oh. Okay, so muscle tissue, generic. Okay, nervous tissue. This is the other thing, one of the other elements that is needed to make up an organ, is types of nervous tissue. And basically these 2 types of cells, neuroglia and neurons. And let me show you some pictures. I'll show you, here's a, I've been much better with pictures. So here's a picture of all different types of nervous cells that we might have. There's a neuron, and you can see it's got these axons are the branching out of the neurons. And then we have various helper cells, nervous cells that are helper astrocytes, oligodendrocytes. Here is another helper cell. So we have a lot of different types of nervous cells that we would find in any type of organ. Uroglia neurons has a maximum of intracellular materials. It's very irritable, obviously. So you're going to have, and the way